So in this video I'm going to start off by looking at specific charge and atomic structure, and then I'm going to go on to look at photons and photon energy. So to get us started with atomic structure, there's a few new terms that you won't have come across when we were doing GCSE. So the first one is the idea of a nucleon. So a nucleon is anything you find in the nucleus of an atom, so it would be a proton or a neutron essentially. And where we use that is actually inside Nuclide Notation. So this is an example of, or the general case of Nuclide Notation. And you see it on a periodic table in a slightly different format. So this A is the nucleon number, so the number of protons plus the number of neutrons. And this Z here is the proton number, so just the number of protons. So to give you an example of a Nuclide notation, for carbon 12 it looks like this, and what this is telling you is that carbon has 6 protons and it has therefore 12 nucleons, or which would mean it has 6 neutrons as well. So isotopes, they are atoms of the same element with the same number of protons but a different number of neutrons. So an example of that would be carbon actually has another isotope, which is carbon 14, and this is what's used in actual carbon dating. So different elements can have the same number of protons, which is what makes them the same element here, but they can have different numbers of neutrons. So this has got 8 neutrons, whereas this has got 6. The last thing we're going to look at is specific charge. So this is the total charge of a particle divided by the total mass. And this was first used when they were looking at electrons, when they first discovered them, because they didn't know either the charge or the mass, so they calculated this specific charge instead, and then later developed that to find mass. But it's quite useful for comparing different atoms, ions, and particles. So that's the key terms. So first of all, let's look at Nuclide notation. So in the previous example, I showed you carbon 12, and intentionally, in terms of stating it, this is what you would do if you're asked to state the Nuclide notation. So you state it like this, showing nucleon number on the top and proton number on the bottom, and the atomic symbol next to it. In terms of what they tell you, the 6 tells you there's 6 protons, the 12 tells you there's 12 nucleons, so therefore 12 minus 6 gives you the number of neutrons, which is 6. In terms of calculating the specific charge, I said earlier that that was the charge divided by the mass. So you start off with the nuclide notation. So we want to do it for a lithium 1 plus ion. So the nuclide notation for lithium looks like this. So there's 6 protons, 7 nucleons, therefore 4 neutrons. So to get the total mass, you've got 4 neutrons, 3 protons and 2 electrons. There would be 3 if it was a lithium atom, but it's lost 1 electron to become a 1 plus ion, so there are now only 2 electrons. And then this data here is in your formula sheet, so the mass of a proton and a neutron is this number here, the mass of an electron is this number here, and when you add them together you get this number. In terms of the total charge, here we are using the actual charge, not the relative charge. So with protons, we normally just say they have a charge of +1. But what we're actually meaning to say is that they have +1 of the magnitude of an electron. So magnitude of an electron is 1.6 times 10 to the minus 19. We've got 1 of those overall, because we've got 3 protons minus 2 electrons, gives you 1 electron worth overall, but positive. Specific charge would be the charge divided by the mass, and in this case you would get this number here. You often get to the 10 to the power of 8 kind of numbers, so it's a useful check. In terms of looking at something different, maybe looking at an oxygen 2 minus ion. So here, when we're looking at the total mass, the key difference here is when it's an oxygen atom, it would have 8 electrons, so they balance out the protons. To become a 2 minus ion, it's gained 2 electrons, so now it's got 10 total electrons. I've been a bit sloppy with my nuclide notation, because for some reason there's still an Li, which is a bit sloppy. So it should look something like that for an oxygen atom. And then we put the numbers in, so we've calculated the total mass, we've got the total charge, because we've got 2 electrons, so 2 times 1.6, but remember it's going to be negative this time because it's got a negative charge on it. Okay, so that's specific charge. So let's move on to look at different decays. Now, decays occur in nature because they're trying to make something that's unstable become more stable. So the 4 different types of decay that we're going to look at are these ones. So we've got alpha radiation, we've got beta minus, beta plus, and gamma. You also might have come across electron capture when we were looking at some of the Feynman diagrams. This is another kind of decay as well, actually. So it's a way of dealing with a proton-rich nucleus, but it doesn't come under the category of these general types of decay, which is why I didn't keep it in this list. So in electron capture, what happens is a proton in the nucleus captures an electron in the inner shell of the atom, forming a neutron and an electron neutrino. But I'm not going to go into more detail on this one. You've already seen the Feynman diagram for that. But in terms of the main 4 types of radiation, you should have come across these at GCSE. So alpha radiation, you have a nucleus has too massive, so it emits an alpha particle, which is the same as a helium nucleus. So it's 2 protons and 2 neutrons gets emitted. In beta minus radiation, a high-speed electron is emitted, which is minusly charged, which is why it's called beta minus. In beta plus, a high-speed positron is emitted, so it emits a positive particle. And in gamma radiation, a high-energy gamma photon is emitted, but you don't actually get any nuclear change, so no protons become neutrons or neutrons become protons or anything like that. So let's have a look at those. So we use these general equations for alpha radiation. So what this is showing you essentially is that that's a mistake there. It should be a minus 4 because you've lost 4 nucleons, and it should be Z minus 2 there. So that's the actual correct term for that. So you see here we've got element X. It has nucleon number A, proton number Z. When it loses a helium nucleus, which has this notation here, that would make the nuclide notation decrease by 4, and it would make the proton number decrease by 2 there. So that's the correct decay equation for that one. In terms of beta plus, the overall nucleon number doesn't change because essentially what you have is a proton turning into a neutron. So what you can see here is that the proton number has decreased by 1, which shows you've lost a proton, but because it's changed into a neutron, the overall nucleon number hasn't changed. This is how you show a positron, so you show it's plus 1, so for the charge, and then what you'll notice is these numbers always add up, so all the Z numbers always add up and balance on both sides, and all the A numbers add up and balance on both sides. In terms of beta minus, the key difference is you actually gain a proton because a neutron becomes a proton, and then you release this electron to balance up the charge. And then in gamma radiation, you've still got the same element X on both sides, but you just emitted a gamma photon, and it's given this symbol here. So those are the decay equations for it, and they show you what happens to it in terms of protons become neutrons or neutrons become protons. Okay, so in terms of these, it's important in order to look at these in terms of interactions and decays and in terms of Feynman diagrams that we know the key properties of each of the particles. So an alpha particle is made of 2 protons and 2 neutrons, so it's 4 baryons, so it has a baryon number of 4. It's got 2 protons, so it has a charge of plus 2, but it's not got any leptons involved, so those are all 0. Beta minus is a lepton, so it's not got any baryon number, but beta plus is positively charged. However, it's an antiparticle because it's a positron, which means it has an electron-lepton number of minus 1. It's not a muon or tau type, so those are 0, just as all the others are not muon or tau types. Beta minus is minus charged, but it's an electron, so it's a normal particle, not an antiparticle, which makes it plus 1 in this column. Gamma is none of these. It's obviously you came across photons as an exchange particle. They don't fit into the category of hadrons or leptons. They're actually something completely different. So they would be zero in all of these categories. In terms of looking at photons, which we're going to move on and look at, there's a couple of key processes you need to know about. So annihilation is when a particle collides with its own antiparticle and their mass and energy are converted into photon energy. So let's have an example. An electron collides with a positron and it's going to produce 2 photons of energy, and it always produces exactly 2 photons of energy. Just a word of warning, if an electron meets an antiproton, this does not annihilate. It's only when a particle meets its own antiparticle that you get annihilation. Pair production is like the opposite of that, so it's when you have a photon and actually it produces a particle-antiparticle pair. And it can only do that if it has sufficient energy to produce them. And that energy is determined by these 2 constants here, the rest mass and the rest energy. So the rest mass is the mass of a particle when it's stationary, and when we're looking at this kind of level, actually mass is not a constant. Actually mass changes, so as you increase your velocity, your mass changes. So that's why we define this concept of rest mass. So when a particle is stationary, it has this amount of mass. And in terms of making this relevant to these 2 stages, if you have mass, that mass is a form of energy, which Einstein's famous E=mc² equation calculates. So if you have a certain mass, that means you have a certain amount of energy. So when these 2 electrons and positrons annihilate each other, they release energy equal to the rest energy of both particles added together and the kinetic energy. And in order to pair produce a positron and an electron, you need energy equal to the total rest energy of these 2 particles in this photon, otherwise it can't happen. So the last thing is we need to be able to do things with photons, so we need to be able to calculate their energy. And there's 2 parts we need to know about here. So to calculate photon energy, you need Planck's constant and you need frequency. So energy is the Planck's constant times the frequency. So Max Planck was one of the first scientists to work in the field of quantum physics, which is why he gets honoured with a constant in his name. And this is in your formula sheet, and that's where you can find it. And essentially it's the ratio between the energy and the frequency. So sometimes, just to be a bit difficult, you don't get given the frequency. So what you need to do is actually work out the frequency from the wavelength. So because this is electromagnetic radiation, we know the speed is the speed of light, so 3 × 10⁸ meters per second. And then once we know that, and we know the wavelength, we can calculate the frequency. So it's another way of solving potential problems.